In this tutorial, we will see how we can select the best line that can fit to a particular data, which one can give consistently good predictions for the new data points, that is testing data. We will give you simple intuition behind it without any code or mathematical calculations. So let's dive in. Let's do the quick recap from the part 1 of the video on what is machine learning. So let's plot this data on the graph, and here the red dots represents the training data. We can have this line which can fit this data, or we can have this line that can fit the data, or this one, or this green curve line. Which one fit the data well? Machine learning methods helps to evaluate which one of the above line or mathematical function is best fit and can be used to consistently give good predictions about the rental values for the new houses, which is represented by new data point or testing data. So let's dive in. Given this data, we see that as the area of the apartment increases, its rent also goes up. It looks that there is some level of correlation between the area and rent of an apartment. We can fit a black line to the data to show the trend of this particular data set. For example, if someone wants to know the rental value for the apartment of this much area, and we could use the black line to predict the rental value, then this is the predicted rent. This black line is a function of machine learning because we can use it to make predictions. In general, machine learning is all about classifications and making predictions. In machine learning, original data is represented here by the red dots and is also known as training data. So the black line is a fit to the training data. Alternatively, we can also fit the green curve line to this training data. Here we can see that the green curve line fits the training data better than black line. But always remember that the goal of the machine learning is to make predictions. We need to decide if the green curve is better or worse than the black curve for making predictions. We can evaluate the performance of both these lines using the testing data. The testing data here is represented by blue dots. So we find a particular blue dot as a testing data, and then we find another one and another blue dot and the another one. All these blue dots represents testing data. We use testing data to compare the predictions made by black line with the predictions made by the green curve. Let's start by seeing how well the black line predict the rental value for these blue dots, that is testing data. Here is the first apartment in the testing data. And this is the size of the apartment. And this is the rental value of this particular apartment. However, the black line predicts that if the area of the apartment is this, then it should have a lesser rental value. So let's measure the distance between the actual rental value and the predicted rental value for this particular apartment, and save the distance between the actual and the predicted rental value on the right while we focus on the other data points in the testing data. Here is the second data point in the testing data, and this is the actual size of the apartment, and this is the actual rental value of this particular apartment. So we measure the difference between the actual and the predicted rental value of this particular apartment and add it to the one we measured earlier for the first data point in the testing data. Then we measure the distance between the actual and the predicted rents for the third data point in the testing data. Then we measure the distance between the actual and the predicted rental value for the third data point in the testing data, and add it to our running total of the distances between the actual and the predicted rents by black line. Then we do the same for the fourth data point in the testing data and add the distance to the running total for the black line. This is the sum of all the distances between the actual and the predicted rental value predicted by making use of black line. Now let's calculate the difference between the actual and the predicted rental value using the green curve line as our predictor function. Now let's remember that the green curve line fits the training data perfectly, that is overfitting the data. So just like before, we calculate the difference between the actual and the predicted rental value. We do the same now by using the green curve. This is the actual rental value of the apartment. And this one is the predicted value using the green curve. And just like we did using the black line, we will keep track of the distances for the green curve line over here. Then we do the same thing for the blue data point in the testing data. Then we do the same thing for the second blue point in the testing data. And then we do the same thing for the third data point in the testing data. And calculate the distance between the actual and the predicted rents and add to the running total. And do the same thing for the fourth data point in the testing data. And calculate the distance between the actual and the predicted rental values. And add to the running total of distances, that is difference between the actual and the predicted rental values. This is the sum of the distances between the actual and the predicted value if we make use of green curve as our predictor function. So here we have seen that the sum of the distances is larger if we make use of green line as a predictor function as compared to the black line. Mini concept number 1. Sum of square residuals is the difference between the actual and the predicted values. Machine learning methods tries to find a mathematical function which has the least sum of square differences. Mini concept number 1. Sum of square residuals is the difference between the actual and the predicted values. Machine learning methods tries to find a mathematical function which has the least sum of square differences. Machine learning helps to find a particular line or a mathematical function that can fit a data in such a way that it can approximately predict the values of the new data point. In other words, even though the green curve line fits the training data perfectly, then the black line did a better job in predicting the rental values with the testing data, which is represented by blue dots. We would choose the black line as our predictor function, as the sum of square residuals is lesser as compared to the green curve line. However, there might be cases where the curved green line might perform better as compared to the straight black line. Though in this example, the black line performed better and can give consistently good predictions on the testing data sets represented by blue dots on the graph. Few takeaways from this video. This example teaches two main ideas about machine learning. First, we use testing data to evaluate different machine learning methods. Second, don't be fooled how the machine learning methods fits the training data. Remember that fitting the training data well but making poor predictions on the testing data is called overfitting the data. This is clearly explained in our next video, which talks about the detail of bias variance trade-off. If you want to learn more about train trust split and cross validation and what is bias variance trade-off, please stay tuned for our next videos on these topics. TechGenie explains in a very simple and intuitive way how to fit a line to the data.
One of the most essential tools used in predictive analysis is simple linear regression. Predictive analytics attempts to answer the question, what might happen next? Predictive analytics is the process of using data to forecast future outcomes. So, what exactly is simple linear regression? Well, in the simplest terms, it's a statistical method used to understand the relationship between two variables. Think of it as a way to examine a two-dimensional scatter plot of sample points. Let's break it down further. Imagine you're a teacher, and you want to predict a student's final grade based on how many hours they study. In this case, the number of hours studied is your independent variable, while the final grade is the dependent variable. With simple linear regression, we can draw a line through these data points that best fits the pattern. This line, called the regression line, can then be used to predict future outcomes. In essence, simple linear regression is like a crystal ball, gazing into past data to predict the future. It's a powerful tool in the world of statistics and data science. So, with simple linear regression, we can predict future outcomes based on past data. But how does simple linear regression make these predictions, you might ask? Well, let's take a look at the mathematics behind it. At the heart of simple linear regression is a mathematical equation. Y equals a plus bx. Here, y is the dependent variable, the one we're trying to predict. X is the independent variable, the one we're using to make that prediction. B is the slope of the line, illustrating how a change in x affects y. A is the y-intercept, the value of y when x is 0. But how do we find A and B? This is where the method of least squares comes in. It calculates the best fitting line by minimizing the sum of the squares of the vertical deviations from each data point to the line. Essentially, it's all about finding the line that best represents our data. And that's how simple linear regression uses statistical data to make reliable predictions. So, to sum up our discussion on simple linear regression, we've learned that it's a statistical method used to find patterns in data and helps to predict the future outcome. With simple linear regression, the world of statistics and machine learning opens up a universe of predictive possibilities. Thanks you, this is Tech Genie signing off.